So we were talking about Euclid's Elements last time, and that's the only picture I could find of Euclid. He looks sad.
The weight of all that knowledge in his brain must have been overwhelming.
Yeah. I just realized I should kill the lights that are glaring up. So a couple of reminders. I think I've said this already about 9 times. The first 2-page paper is due next Friday. The wiki entry revisions are due by the end of the day, so I'll take them as late as midnight. Get it done before the weekend. I was on jury duty yesterday, and I thought, I've got all this time. I'm gonna get those papers graded. I did. So yeah, I expect to spend the weekend with your papers in a nice close sort of. Anyway, yeah, I'm gonna get it done this weekend. So I'll get you those comments on the second papers, and then we'd look for revisions a week after that. So it's October 2nd. So I think we'd already gone through this slide, but I just wanted to kind of get us rolling again. The 13 books of the elements, 1 to 6 are the plane geometry things. 7 to 9 is number theory. 10 is the theory of irrationals. And then the last 3 give us 3-dimensional geometry. I showed you the platonic solids, and that's sort of the capstone thing in there. They prove that there's just 5, which, now that's an interesting piece of calculation, thinking about it. Why just 5? Well, one problem that you'll realize pretty quickly is if you're going to make a solid object, you have to have at least 3 things come together in a corner. Right? That means once you get up to hexagons, you're kind of screwed. You know why? If you put 3 hexagons together, what happens? At the joint 360. Well, it's exactly equal to 360, right? And they lay flat. In fact, there are tiles that are hexagonal shaped that will tile the floor. So 7 gons, 8 gons, all those are immediately out because you can't fit 3 of them together in a corner. And hexagons are out. So you've got to work with triangles, squares, and pentagons. And then it comes down to how many things can you fit in a corner. If you use triangles, you can either fit 3 in a corner, get the tetrahedron, 4 in a corner. What do you get if there's 4 sitting in a corner? Cube. The triangles, though. The triangle facing. That's the octahedron, dual to the cube. So think about the top of the pyramid. The top of the Egyptian pyramid has 4 triangles. If you put 5 triangles at 5 equilateral triangles in a corner, each one of them has 60 degrees, so that only adds up to 300. It means it should be able to fold up. And when you've got a kind of a cone of 5 triangles meeting at a point, well, it actually is 3-dimensional. It's not flat. If you had 6 of them, you'd be back in the flat. 5, and that makes the icosahedron. If you bring 5 triangles together in every corner. So that's a kind of an outline of the proof. You exhaustively go through all the possibilities and show that you can't use anything bigger than pentagons. Oh, I didn't talk about those. Yeah. Anyway, the thing about definitions and postulates is where I really want to get to. I think my favorite definition in all of Euclid is this phrase, which is in Greek, so no. But in English it says, a point is that which has no part. Okay. What do you think they were saying? A point is that which has no part. I mean, they were trying to. The point is, the aim of this discussion is to talk about geometry. So you need to say, well, what are the things we're going to work with? Points, lines, circles, the basic elements of geometry. So you have to define those things. Euclid was facing something that now we know is a fundamental problem. You can't define your fundamental things. There have to be certain atomic terms that are undefinable. You can show people this is a point, and they go, okay, I think I get what you mean by a point. But when you try to make a formal definition of something that is literally atomic, you're just going to sound mystical. And I think that's what happened with the point is that which has no part. I think he was trying to say it has no volume or no size. So a point has zero size in any direction, has no volume. I mean, there's other things that have no volume. So, let's just talk about these axioms. Once he got through trying to define what points and lines are, and that was stupid. You didn't know it at the time, but you can't. Right? You have to have these undefinable things that you just work with. He began writing axioms about them. Now the first, well, I'm going to show you what the full set of axioms are, but the first three of them are about constructions. If you've got this, you can make that. It tells you how to sorry, not how to, but that it is possible to. Always, for instance, if you've got a line segment, just from A to B, just the finite line segment, you can keep rolling. You can make it into a line. That is, go from a finite thing to an infinite thing. That's fair enough. And the idea is you'd have to keep sliding your ruler down and drawing more of the line, but you could do that, at least in principle. But postulate 4 has a weird character to it. It says something about congruence. So does everybody know what it means for two angles to be congruent? The same measure? So it literally means that you could slide them around in space, maybe move both of them, maybe move one over where the first one is, and they'll lay right on top of each other. That's what it literally means. That motion in space will allow you to set one on top of each other. So this fourth postulate says all right angles are congruent.
Right angles.
Seems like it's an obvious statement, but what he's really getting at is much weirder. He's getting at the idea that if you draw a right angle over here and a right angle over here, when you slide them over and try to lay one on top of the other, they're not going to mismatch. That is, right angles at one place in space and right angles at a different place in space are the same. This is something physical. I think I mentioned this in the next slides. Maybe I should move on. Wait a minute. Oh no. Tell me I got the wrong version. I think I'm just taking my slides out of order. So the fourth and fifth postulate, different nature. This is saying that geometry is homogeneous, that the plane's properties, in particular orthogonality, don't change if you're at one end of the plane versus the other end. You know, I'll make this comment now, and I'm thinking I have it on a slide later. In physics, they make this assumption all the time, that the rules of physics, the laws, don't change. If you're here on Earth, E equals mc squared. If you're out at Alpha Centauri, you still mc squared there too, right? There's no variation in the laws from one place to another, and also from one time to another. Right, so the same laws that we think of now as holding in our universe held right at the Big Bang. I'm not so sure if that's a valid assumption, because the character of the universe was really very, very, very different at the instant the Big Bang happened. But that's the assumption they make, and mostly because what other assumption could you make? Just to try to be fair, you think, oh well, I'm hoping it's the same everywhere. And you often see this in Star Trek episodes. They go to some region of space where things are different. And so for science fiction, that makes good sense. I suppose it helps build a nice story. But for trying to figure out reality, it's not that bad. Okay, so the fifth postulate. This fifth axiom of Euclid's is literally famous. They literally call it the famous fifth, or parallel postulate. It states that one and only one line can be drawn through a plane parallel to a given line. First of all, no, it doesn't. That's a quote from the MacTutor History of Math Archive, and that's not what Euclid's fifth axiom says. But it's equivalent to that. So we'll come to what it really says, and then show that, well, at least begin to believe that it's equivalent to this idea. So he picked this particular axiom, the one that's not the one that's on the screen right now, and that makes the geometry he constructed the one we call Euclidean. There are other geometries, and they didn't happen until the 1800s. In the 19th century, Lobachevsky and wait, there's another guy, Bolyai, came up with a negatively curved space. So the planar geometry of Euclid is called neutral geometry. Well, I'm sorry, I should say that differently. Neutral geometry is what you get if you don't throw in this fifth postulate. So just use the first four axioms. Flat geometry, or zero curvature geometry, is the thing that Euclid gets when he adds on his fifth postulate. And the other possibilities are to have positive curvature or negative curvature. So the one I just mentioned in the 1800s, Lobachevsky and Bolyai came up with is a negatively curved geometry. There's also Riemann, who we're actually going to talk about later on in the course. We won't talk about Lobachevsky so much, but Riemann came up with a positively curved. So we'll get through the rest of them. The other common notions, there's a couple of things that he calls common notions. I think what he's talking about is axioms of just more basic arithmetic in geometry. Do you know what this last example is called? Things which are equal to the same thing or equal to each other?
The transitive property.
That is the transitive property of equality. That's what we call it nowadays. He just had a phrase for it and said it was common. So some of the impacts, the importance of the thing. This is not like Euclid produced this all by himself. It wasn't that. He was looking at the works of Eudoxus and Thales and several others, and taking all their results together, but didn't just report what they had done. Sometimes those earlier mathematicians didn't give proofs at all for their things. Sometimes they gave proofs that were pretty sketchy. So he really made it rigorous, right? He made the arguments stand on their own. So because of that, his approach became really the model for doing math, this axiomatic approach. And it's still today true that that's what people view, how people view it. It was the geometry textbook for 2,000 years. You know? That's pretty awesome. I mean, I still think people study the elements. They try to follow through all the little arguments that he goes through in the first several books. I'm not sure if many people go past book 6. I've noticed that there's a tendency, when I read articles about mathematicians, there's this phrase over and over again. They say, this so-and-so studied the books of Euclid and mastered the first 5 books by the age of 7. Things, or whatever, some ridiculous age. They always try to make each one seem like more of a genius than the last. But that's the phrase. There's this really famous, although probably largely inaccurate, history of math book called Men of Mathematics by Eric Temple Bell. I read that when I was a kid, and it seems like every one of these great masters of mathematics from the Renaissance and going up into modern time, he has this thing about how they studied Euclid's elements and had mastered it at some very young age. Okay, so let's talk more about the fifth axiom. The first 3 constructions. 4 is the homogeneity of space. There's the slide that I was mentally thinking about, that comment that physicists do this, something similar to 4 when they're saying that physics is the same everywhere in space. But axiom 5 is horrible. Okay, so here's the actual axioms. Number 1, a straight line segment can be drawn joining any 2 points. Sure. But notice what it's saying can be done. It's not saying there's a line through any 2 points. It's saying there's a line segment. Just a segment. The second axiom is the one that hits lines. If you've got a segment, you can extend it in both directions to make an infinite straight line. Axiom 3. It's not so bad. If you've got a segment, you can use it as a radius. So you can just imagine spinning it around one endpoint or the other and make a circle. The two tools that they use in geometric constructions are a ruler. I just said ruler, didn't I?
Yeah, compass.
A straight edge. I didn't mean to say ruler, I meant to say straight edge. Do you know the difference between a ruler and a straight edge?
It's actually straight.
Well, they're both straight, but one's got marks on it. We don't want any marks. So the straight edge just is an unmarked ruler. Right? That's the tool you're allowed to use, and that's really the thing that lets you extend a line indefinitely in any direction. You can keep sliding the straight edge down the line and draw a little more of it. The compass is what lets you do the construction in Axiom 3. If you have a line segment, you can set your compass to the size of that line segment and rotate. All right angles are congruent. That's this core that says that it doesn't matter where an angle is. You get the same measure if you move it around. And then ready? Just think. Yeah. Did you notice every other one fit on a single line, or most of the two? This thing is 4 lines. Let's read it. If 2 lines are drawn which intersect a third in such a way that the sum of the inner angles on one side is less than 2 right angles. Holy hell. What's 2 right angles?
180 degrees.
180 degrees, or pi if you're in radians. So we're saying let's make a picture, I guess. You've got 2 lines like that, and a third line like that, and these angles on one side don't add up to 180. And that's what they're saying. And in fact, they add to less than 180. Well, if that's the case, then the 2 lines inevitably must intersect each other on that side if extended far enough. You see how my picture looked like these lines were kind of tilted towards one another? Well, if you go far enough out there, it's apparently way off the board, but if you extend them both far enough, they're going to hit. That's what it says.
Okay.
So, people hate this postulate. Euclid himself clearly did not like this postulate because he didn't use it at all at first. He avoided using it, and I suspect he only added it in when he got to his 29th proposition, and he needed this. That's when he said, all right, I can't find any other way to prove this without some extra axiom. So let me go back and revise the beginning of the book and put the 5th axiom in there. I was really hoping to go with only 4. Now, I'm picturing that was how Euclid felt.
Was the 29th proposition that actually needed that?
I don't know. I never looked that up. That's a good question. There has been a cottage industry, seriously, for 2,000 years. People have been trying to figure out, could we maybe prove this using the other 4? Because it's really a very different sort of statement than the first 4. The first 4 are quite easy. This is quite difficult.
It's highly specific.
So people tried and tried and tried to prove it using the first 4 axioms. And that would mean, if you could do that, that would mean you really didn't need 5, right? It was just 4 axioms was enough. So they tried and never did it. Finally, in 1868, Eugenio Beltrami showed that it is independent of the other 4. And independence is actually a really interesting and modern idea. Independence of statements means that you can't prove and you can't disprove the one via the others. So 5 being independent of the first 4 axioms means it's not possible to prove. And we can prove that it's not possible to prove 5 from 4. But it's also not possible to disprove it from 4, from the first 4. That's interesting because it's not entirely true. There's a little flaw in that statement. So this is an of what's called meta-mathematics, by the way. Using math methods to study math itself, right? to talk about what possibly could be proved and what possibly cannot be. Oh yeah, that's there. I just said what independent was. So there's a dude named Playfair. I thought somehow that the name Playfair's axiom had to do with you should play fair. So I was trying to make a joke in the title of this slide, but there's actually a person by this name. And I don't know if anything else they've done except give an equivalent version of the fifth axiom. So that's the statement that was in the slide where I quoted back to you. Okay, so Playfair's axiom says this: if you've got a line and you've got a point that's not on the line, there can be only one line that goes through this point which is parallel to that one. Sorry, did I give you your red pen there? Or your green pen?
I think so, I grabbed it.
Because I was planning to give it back to you. Nope, I didn't. Here it is. See, I mean, there's a bunch of lines that go through this point, right? I could go this way or that way, but if there's exactly one that goes sideways to the other line that is parallel.
Are we in R3 or R2?
This is in the plane. So all of Euclid's stuff in the first 6 books was, or was it 5? Anyway, the first several books was plane geometry. So, okay, doesn't that seem obvious that there's one line that goes through that point that's parallel to the original line? It feels like, how could you do something different? So, it's a little bit unfair that Playfair gets his name associated with this axiom, because there's old writing from 400 AD that's like Proclus that shows that same axiom. So the ancient Greeks also knew this variant that was equivalent to the fifth axiom. Weird. So this is the formal statement of it, and I want to point out that there's something a little funny about this formal statement. It says, in a plane, given a line and a point not on it, at most. So at most, one line parallel to the given line can be drawn to be a point.
Why is it not exactly one?
Why is it not exactly one? At most.
You have half a line?
Why can I do none?
There has to be one.
There has to be one line. I mean, you know, this is math, so we can't just say shit and go, well, there has to be. We got. Sorry. Yeah,
Is
so,
that
I mean,
non-Euclidean geometry?
well, that's the problem. You get into the non-Euclidean geometries if you say the two ways to negate there's one is there aren't any, and there's more than one. Playfair's axiom seems to be saying that they know there's at least one, so he's saying now there's at most one, and that's true. The first 4 axioms apparently can be used to say there is at least one line. Yes. They don't have enough to get that it's unique. So that's why you need to fit that. And that's actually, well, that's a very fine point, to be honest. So I didn't know this. I got to tell you, I always thought it said there's exactly one line. So there is a line through the point, but Playfair's axiom and Euclid's fifth axiom both will tell you that that line is the only line for that. So there's some interactions, and this is saying that really the Playfair's axiom and the first 4 are not entirely independent. There's some interaction there. Without the interaction, this is the version I want to think about, without dealing with the interactions with the other things. Just think about axiom 5 by itself and formulate it the way Playfair would have us do. In a plane, given a line and a point not on it, exactly one. That's what I like to have. There's one line. And the reason I want to emphasize that is to think about how can it not be true? So the negations, there aren't any lines, and there's more than one. Okay, so this is weird. In certain geometries, there are no parallel lines. You can't even have, there's no such thing as parallelism. Can you imagine a world like that?
Inside of a balloon?
So you actually live on a world like that. The surface of the spherical planet that we live on. Is anybody a flat Earth adherent here?
Yes,
Yeah.
absolutely.
So the fifth axiom holds for you, but on the Earth that the rest of us inhabit, there's no such thing as parallel lines. You can't have parallel lines. Well, first off, we've got to get ourselves past the same problem that Euclid had in defining things that are hard to define. What's a line?
It's a jigger that just pulls one.
But you're going that way.
Yeah.
So if you're on the surface of the earth and you just keep going that way, what happens eventually?
Go back around.
You come back around to where you are, right? You come up from behind yourself and go, boom. What sort of path did you follow? If you literally walk, maybe you're the Flash and you can run around the world fairly short. What sort of path? That's a circle. Do you know that they call it a great circle?
So it's a minor circle.
Because you can't get any bigger and stay on the earth. If you had that circle, right, you make it out of steel. Now add 1 inch of extra material. Now it's floating up off the surface.
Okay.
It's still a circle. So if you're on the surface of the earth and you're a circle, that's as big as you can get. Think about it from the North Pole. Right? You can start at the North Pole with a tiny circle, right? And then as you go down, making your circle bigger and bigger and bigger, once you get to the equator, it's as big as it's going to get, because then it starts shrinking again from there. So there's this sort of maximum size for circles on the earth. And the equator is one of them. Great circles.
Well, what's a minor circle?
Well, anything other than a great circle. We don't call them, I think they're called lesser circles. But I'll give you an example. We live at latitude 39 degrees. Sounds about right. 36? Okay, so that latitude line does not go completely around the Earth. In fact, the plane that line is on is offset from the center of the Earth. We're up in the northern hemisphere. So the lines of latitude are not great circles, except for one line of latitude. Anybody know the line of latitude? The equator, right? How about lines of longitude? Are they great circles?
So great divider, whatever it is.
Yeah, the Greenwich Meridian.
Yeah, that's what it is. Yeah, you're on the same picture.
Yeah.
Well, all of the lines of longitude go completely around the Earth.
I'm stupid. Never mind.
What?
Yeah.
Oh, you were thinking it was just the...
I'm thinking about
Greenwich.
just one. Wow. So
Yeah, they're all, no, because you can take that one and spin it around the North Pole, right? If you ever see old globes that are in a frame, they usually have this sort of line, it's a
the spinny
circle that goes around the globe, and there's an axis on it that the globe spins on. And as you spin the globe, you can bring any place on the Earth to that arc, and that arc is normally measured as angles on it, right? So you can tell what latitude you're at, and also, the globe itself will have longitude lines. All right, so you want to do a silly joke slash puzzle?
Absolutely not.
Sure. No, Jeremy said to do this. So a man walks out of his house. He goes 1 mile due south, then 1 mile due west, 1 mile due north, walks back into his house, gets his gun, and shoots a bear.
North Pole.
You're so smart. Yes. Right, so the usual thing is, what color was the bear?
White.
White. Yeah. Okay. So this is an interesting point, because I want you to think about the triangle that we just described. He's on the Earth. Okay. There's the North Pole. He walked due south, then due, whoops, better do it in a different position. He went due south, just away from the North Pole, right? I should have put an N on this. Then he went due west, and you notice he had to curve to do that. Go due west, right? And then he had to go due north and come back into his house. What angles are on those, on that triangle?
It's more than 180 degrees.
Doesn't it look kind of blown up, a little fattened up? Yeah, and it is more than 180 degrees. This part in here is 90, and so are these. Now, there's a little bit of a cheat here, because 2 of these things are lines and 1 is not. You see which 2 are great circles and which one is not a great circle?
The jigger at the bottom.
The guy at the bottom, yeah, that's a minor circle. If we extended it around, it's just a little radius 1 circle at the North Pole. So this is not a line. I have a bad feeling I'm drawing here where the camera won't pick it up. Maybe I should move. But I can describe a circle, I describe a triangle with 90-degree angles on it on the Earth. And everything's great circles, so this is definitely weird. Go from the North Pole all the way down to hit the equator, and then go around the equator, and then go back to the North Pole. So you can make this 90 degrees at each one of the three corners. So that's kind of messed up. You know what the sum of the angles of a triangle is supposed to be.
That's one positively curved space.
Well, that's what we're on. We're on a positively curved space. So that's where we live. So you've probably heard of Gauss. If not,
We will see.
we haven't talked about the history yet, but he's one of the people we'll cover. But you've probably heard about him in Calc 3.
Linear algebra.
Calc 2, linear algebra for short. Guy did an amazing amount of interesting stuff. One of the just weirdo projects he did was got teams of men together to put up bonfires on the tops of mountains that are really far apart in Germany or Switzerland. And then they carefully measured from one bonfire to the other what the angle of the thing was. Because he was interested in figuring out whether not the Earth's, he knew the Earth's curvature was such that we would get that angle greater than 180, but if you're up on these mountaintops, you're just using light beams. Those light beams aren't curving along the surface of the Earth. So we're looking at these bonfires and measuring angles. You're using visual light to see something. And he was interested to know whether this triangle that you could create kind of floating in space had a sum of the angles equal to 180 or less or greater. He really conducted the experiment. I think it's kind of cool that he tried, because the world we live in is actually positively curved, just because we live near a gravitational field. The Earth is a fairly heavy thing, and that's what gravity is all about, the curvature of space-time. So he should have, if he had lasers and really good little microscopic targets, he would have been able to measure that curvature. But he had bonfires and guys with sextants, so it was
What does negatively curved space look like?
So let's talk about the positive and the negative. Positive curve means if you go either in the x direction or in the y direction, the curvature goes the same way. So if you're on a ball, it curves down or down. Right? If you're on a Pringle chip, everybody appreciate what a Pringle chip looks like? In one direction you'll curve upward, in the other direction you'll curve downward. So when there's a mismatch between the directions of the curvature, you get negative curvature. What basically, in fact, this signed curvature goes to Gauss. He defined what's now called Gaussian curvature as the product of the maximum and the minimum curvature. So if the minimum is a negative number, this product with the positive will be negative. So you get negative Gaussian curvature on saddles, in the passes between mountains. Find somewhere on your body that's got negative curvature. Find a region, elbow, curves one way that way, and the other way this way. Neck is a good place. Hey, you got any spots on your body that are positively curved?
Hooray!
Yes, of course. the head, right? Curved both directions. We can go with more examples, I guess. It's embarrassing. So, do you see there's no parallels? If you have two of these great circles, they got to hit each other. In fact, they hit each other twice. The way two lines of longitude will hit both at the North Pole and the South Pole. So there's no such thing as running completely parallel and not running into one another on a sphere. The other kind of geometry has all kinds of lines that are parallel. So that is, you can draw more than one line. It looks a bit like this, but you see the idea of lines has to be made more general. You have this other point, there may be lots of lines that go through it that are parallel to the first guy, but they're just going to have to be curves, not what we would call curves. I do this fairly frequently. Go to Home Depot to pick up wood for some project I want to do, and they have big piles of wood, but some of it's crap. So what you do is you get at the edge of the wood and you look down it, and when you're looking down the length of the wood, you can tell if it bends. It's very obvious. When you're just holding it like this, you may not detect that. So this is something that we all probably have done at some time, to sight down a thing to tell whether it's bent or not. What you're doing is using light, the path of light that's entering in your eyeballs to define what straightness is. So this became an axiom for a certain very important person. You got an idea who I'm thinking of? Albert Einstein. He said, look, what we've got to do is just use light beams as our defining thing for straightness. So lines, from his point of view, lines are light paths. This is not in my slides, but I got to mention it while we're here at this moment. We just had a really nice solar eclipse in the U.S. The biggest justification, the biggest evidence in favor of Einstein's general relativity theory happened during a solar eclipse. And let me kind of roughly draw the geometry. Let's say that's the sun, and here's the Earth. The Earth is really way smaller than the sun, but I'm just going to draw them roughly the same size. The moon gets in the way, so you're not blinded by the sun. And what they did was set up a telescope that looked just past the edge of the moon, and so just past the edge of the sun. And that telescope, the light entering that telescope followed a straight path by Einstein's rules, right? And he located a star. Well, really the stars are way, way farther out, but I've run out of space on the board. The problem is, they knew where the star was, and it wasn't there. It was here.
Yep, we bend space-time.
That's right. The path of this light had to be bending while it was going past the sun.
Oh, God.
And it was by the exact amount that Einstein predicted. Right? He told them, look, that gravity field of the sun is going to bend the paths of light beams. So straight lines look bent. Well, that's not a feature of the line really being bent. That's that the space we're living in is bent. That's the interpretation of general relativity. Okay, so this other thing where instead of positive curvature like that, with negative curvature is weird. So, has everybody seen this little image before?
Yes.
Oh yeah, the famous Dutch artist, M.C. Escher. It's really pretty. I mean, it's interesting.
Is it a fractal?
Well, it's got some infinity-ness to it, right? It's called Angels and Demons, and you see that there's two different sorts of tiles on here, and the angels, the white ones are angels, and then the space in between the angels is the demons. You see? Okay, so if you actually look at a tiling like the tiling on this floor, does it look like that? I don't know. There's 4 edges on the tiles. How many edges are on these tiles? 3. It looks like 3s, doesn't it? The angel has 3 demons that are on the sides of her. No, they've made the edges kind of fanciful so that you get the picture, right? But basically, that's a tiling of triangles. That's okay. We can still work by analogy. But the tiles that are right under my feet, the same size as the tiles over there by the door?
Yeah.
Yeah. Because you know that they are, right? But do they look the same size?
Not from this distance.
Yeah, those guys are in the distance, so they seem smaller. All he's done is take that idea to its logical extreme. These tiles literally get smaller as you go towards the perimeter. So they're fitting more and more in. This is called the Poincare disk model of hyperbolic geometry. So let me quickly give you the disk model and then we're out. The disk model consists of the boundary is a circle, and the straight lines, you've got to define straight lines, right? Well, you can do either things that are complete diameters of that circle, or any arc that crosses at 90 degrees. So you do something like this. That's a straight line. So now, let me put a point and a couple of lines that are parallel to that one. And last thing here, I promise last thing. I've got two lines here that are intersecting. I'm gonna try to find a third line that intersects. Because that way I just, another marker. I just created a triangle. You see the triangle I made right there? What do you think about the angles on that guy? Do they add up to 180?
Yeah.
They look pretty skinny.
One obtuse, is tacky.
Let me show you a bigger triangle then. That would be this one. Go all the way to the perimeter for our sides.
Oh, yeah.
Holy hell, those guys have 0 for all three angles. So it's true, in a negatively curved geometry, triangles add up to less than 180 degrees. In flat geometry, they add up to 180, and if in possibly curved holes, you can tell what kind of geometry you're in by that experiment that Gauss tried to pull off. Yeah, don't forget there's some homework posted for Monday, and try to read 3-4 of them.